In this video, we discussed the analog to digital conversion for digital communication systems. Now let's look at the simple module for digital communication systems. If a source is analog source, such as a continuous time voice signal or any continuous time signal, we need to convert this analog signal or continuous time signal into discrete time. First, we discretize in time, and then we perform quantization. We discretize the value of the signal. So this A to D in digital communications, pay attention, that's not normally we call it analog to digital. It is analog to discrete time. And then we perform quantization. Good quantization schemes can reduce the distortion of the analog signal to digital signal conversion. Normally, there's a design component for the quantization for communication systems. So this module can be discussed in the course. Now let's look at the conversion from the continuous time signal to discrete time signal. I have a figure here, it's kind of small, so I redraw it here. I have a continuous time signal here. It's called xc of t. C means continuous, or x of t, or xa of t. A means analog. All of these notations means that the signal is continuous time. If a signal is continuous in time, we know there's infinite time point here for the signal. And in any system in practice, it is impossible to transmit. So we need to discretize the signal in time. How do we do that? We sample the continuous time signal. Suppose the sampling period is Ts. Every Ts, I obtain one value of this continuous time signal. For example, if I start time t here, I obtain the value of xc of 0 at time 0. And then at Ts, that's the next sampling time. At Ts, I obtain the value of xc Ts. And then at 2 Ts, I obtain xc 2 Ts. At 3 Ts, I obtain the value of the signal at 3 Ts, so on. In this case, this is time. The x-axis is time. By performing sampling operation, we can see this continuous time signal become discrete time. So the time is discrete. It does not contain infinite number of time slot in the real line. If we look at an example here, if Ts equals to 0.1 second, which means that every 0.1 second I obtain one sample, every 0.1 second I obtain another sample from the signal. The concept of sampling rate, Fs equals to 1 over Ts. In this case, is equals to 1 over 0.1, that's equals to 10 samples per second. So in this case, I will obtain 10 samples in 1 second. This is the concept of sampling period and sampling rate. Some people also call it sampling frequency. The same thing. Sampling rate, sampling frequency, that's the same thing. We just explained how we obtain the sampled signal from the continuous time signal. Next, let's express this sampled signal mathematically. Why do we want to express this mathematically? Because we want to look at the frequency domain. I call this sample signal as x delta t. I have a shifted delta function here at multiple of Ts, 0, Ts, 2 Ts, 3 Ts. If we multiply the continuous time signal by the impulse train here, we will obtain the sample signal. For example, at time 0, at time equals 0, n equals 0. So delta t, this is a delta t, multiplied by the signal, what do we have? We have a delta function here, but scaled by the signal value t equals 0. At t at time equals ts, there's another delta function multiplied by this continuous time signal. We have another delta function. The magnitude is the signal value at ts. And at 2ts, that is another delta function, but scaled by the signal values at 2ts here. Therefore, this sample signal is a direct multiplication of the continuous time function by the ideal impulse train.